Ever feel like numbers are trying to trick you, especially with things like sales or stats you see in the news? Well, you're not alone. Today, we're going to pull back the curtain on some of those common math traps that pop up everywhere. Let's dive in. So let me kick things off with a little puzzle for you. It seems pretty straightforward, doesn't it? You increase a number by 20%, then you decrease it by 20%. They should just cancel each other out, right? You should end up right back where you started. Shouldn't you?
Well, the answer is no. The final number is absolutely not the same. And stick with me, because by the end of this short explainer, you're not only going to understand exactly why, but you'll be able to spot this kind of trap from a mile away.
Okay, so to really get why that puzzle trips so many people up, we've got to take a quick step back. We're going to go back to the absolute basics for just a moment. Don't worry, this is the easy stuff, and it'll make everything else just click.
All right, first up, percentages. You know, the word itself kind of gives the game away. Percent. It literally just means for every 100. So if you see 25%, all you have to do is picture a big grid with 100 little squares. 25% is just 25 of those squares filled in. That's it. Super simple, right?
Next up, we have ratios. The best way to think about a ratio is to think of it like a recipe. It's not about how much you have in total, it's all about the balance between the ingredients. So a 2-to-3 ratio of apples to oranges just means for every 2 apples you've got, you need to have 3 oranges.
And that flows right into our next idea, proportion. A proportion is really just a way of saying, hey, these two ratios, they're actually the same. They might look different on paper, but the balance is identical. So that 2-to-3 apple and orange mix is the exact same proportion as having 4 apples and 6 oranges. You've just doubled the recipe, that's all.
Okay, so that's the theory out of the way. Now for the fun part. Let's actually put these ideas to work and see how they can help us solve some real-world problems. Check this out. Here's a fantastic shortcut for figuring out percentages in your head, no calculator needed. Let's say you want to find 20% of 150. Instead of getting bogged down in fractions, just find 10% first. That's always easy. You just move the decimal point. So 10% of 150 is 15. And since 20% is just double 10%, you just double your answer. 15 times 2, boom, 30. Simple as that. And you know what? That same kind of step-by-step logic works perfectly for ratios too. Imagine you need to split 360 rupees in a 2-to-3 ratio. First, just add the parts of the ratio together. So 2 plus 3 gives you 5 total parts. Next, take your total amount, 360, and divide it by those 5 parts to find out what one single part is worth. In this case, it's 72. Now you just hand out the shares. 2 parts is 144, and 3 parts is 216. Done. Okay, let's switch gears a little bit. Now we're going to talk about how different numbers or quantities can affect each other. This is where we get into something called direct and inverse proportion. And really, there are 2 main ways this happens. First, you've got direct proportion. This one's pretty intuitive. When one thing goes up, the other thing goes up too. Think about it. The more pens you buy, the more your total cost is going to be. Makes sense. But then you have inverse proportion. This is the opposite. When one thing goes up, the other thing goes down. Like, the more people you get to help on a project, the less time it's going to take to finish. Here's a classic example of that inverse proportion in action. Let's say 6 workers can finish a job in 10 days. You can kind of think of that job as needing 60 worker days of effort. So what happens if you double your crew to 12 workers? Well, you're going to cut the time in half. It'll only take 5 days. See? More workers, less time. Okay, you've got the building blocks. You understand the concepts. I think we're ready. Let's circle all the way back to that puzzle from the beginning and finally crack the code. So why don't they cancel out? Let's walk through it together. Starting with 100 always makes things easier. First, we increase it by 20%. 20% of 100 is 20, so that brings us to 120. Simple enough. But, and this is the whole trick, when we decrease it by 20%, we're not taking 20% of the original 100. We're taking 20% of our new number, 120. And 20% of 120 is 24. So you take 120, you subtract that 24, and you land on 96. See? Not 100. So the trap is all about the base. The 20% increase and the 20% decrease are calculated on different numbers. The first 20% is based on 100, but the second 20% is based on 120. And that, right there, is why they don't cancel each other out. Now that you know the secret, here are some really handy mental checks you can use. For any problem like our opener, just test it with the number 100. It makes it so much clearer. When you see a proportion problem, just ask yourself, okay, are these things moving together or in opposite directions? And for ratios, your first step should always be to add the parts together to find the total. So there you have it. You've just seen how a really simple, obvious-looking math shortcut can totally lead you astray. And it really makes you wonder, doesn't it, now that you can spot this trap, what other math rules of thumb that we all use every day might be worth taking a second, more critical look at? All right, let's talk about money. And I want you to forget everything you remember from boring math class. Today, we are cracking the code on what's called commercial math. These are the simple but super powerful rules that really explain how money works. So where do we start? Well, it all starts with this one big question. You've probably wondered, right? How does money actually grow? Is there some kind of secret to it? Well, it's not so much a secret as it is a system. And that whole system is built on just two core ideas, two different paths your money can take. And this slide right here, it perfectly captures the whole idea. Just think of your money like a plant. Simple growth is kind of like a little seedling. It grows the same amount year after year. It's steady, it's predictable. But compound growth, whoa, that's like a big tree. It doesn't just get taller, its branches start growing their own new branches. The growth itself starts growing. So let's really dig into these two, side by side. On one hand, you have the straight and narrow path of simple interest. And on the other, you've got this absolute powerhouse called compound interest. You know, understanding just this one difference is probably the biggest key to getting your head around finance. Okay, so simple interest is, well, it's the most basic way to think about growth. It's kind of like you're earning rent for letting someone borrow your money. The interest you get is calculated only on the original amount you started with. We call that the principal, or P. Then you just multiply that by the interest rate, R, and the amount of time, T. It's a really clean, straight-line calculation. Super easy. Let's actually walk through one. Let's say you've got 2,000 rupees, and you're getting a 5% annual rate for 3 years. We just plug those numbers right into the formula. 2,000 times 5 times 3, that gives us 30,000. Then we just divide that by 100, and we should get our answer. And there it is, 300 rupees. That's the total interest you've made over those 3 years. Simple enough, right? Your money grew by the exact same amount each year. But what if it didn't have to? Now let's talk about compound interest, because this is where things get really interesting. This is where the magic happens. Here, the interest isn't just calculated on your original money, but on the principal plus all the interest you've already earned. Your interest starts earning its own interest. It's a snowball effect. This slide gets right to the heart of why this is so powerful. Look, with simple interest, 10% on 1,000 rupees for 2 years is 200 rupees, flat. But with compound interest, after that first year, your new total is 1,100 rupees. So in year 2, you're earning interest on that new, bigger amount. And that little bit extra creates another 10 rupees that simple interest just leaves on the table. And this chart says it all, doesn't it? See that little gap between the two bars? That is the power of compounding in action. And here's the really important part. Over time, that gap doesn't just stay the same. It gets wider and wider, exponentially. I mean it. This is the simple principle that builds fortunes. Okay, so growth is only one half of the story. What about the rules for just handling money day to day? These are the ideas you're dealing with every single time you buy something or maybe plan a trip. First up, something you see on pretty much every single receipt, GST. It's really just a tax that gets added on to the final price when you buy something. It's a totally fundamental part of how most modern economies work. Here's a super simple example. The price tag on something says 1,000 rupees. If the GST is 18%, that means 180 rupees goes to the government, and you end up paying 1,180 at the register. It's just straightforward addition, really. Next up, we've got foreign exchange, or what people usually call Forex. Have you ever traveled or bought something online from another country? Then you've used it. It's this huge, massive global market where currencies are constantly being traded against each other. You know, dollars for rupees, euros for yen, the whole thing. So let's say the exchange rate is 80 rupees for $1 US. Well, your $50 becomes 4,000 rupees. Pretty simple. But here's a crucial pro tip to remember. The bank will always sell you foreign currency for a little more than they'll buy it back from you. That tiny gap, it's called the spread, and that's how they make their profit.
Okay, so we've covered how money grows and how it moves around. But there's another level to this game. Instead of just growing your money, what if you could own a piece of the actual business that's doing the growing? And that, my friends, brings us to shares.
When you buy a share, you're not just buying some piece of paper. You are literally buying a tiny, tiny slice of ownership in a real company. And if that company does well and decides, hey, let's share our profits with our owners, that payout you get is called a dividend.
Now, this is a critical detail, so listen up. Dividends are always calculated based on a share's face value, that's its original printed price, and not its current market value, which, can go up and down every single day. So if the face value is 100 and the company declares a 12% dividend, you get 12 rupees per share. It doesn't matter what you actually paid for it on the market. All right, now that we've got all the core concepts down, let's see how we can put them to the test. Because in an exam, it's not just about knowing the formulas, it's about knowing how to use them smartly and quickly.
Take a look at this. This is a pretty typical problem, right? Now, you could calculate the simple interest, then calculate the compound interest, and then subtract one from the other to find the difference. And that totally works. But on an exam, time is everything. So the real question is there a faster way?
Oh yeah, there is. And here it is. This right here is your secret weapon. For any 2-year period, the difference between compound and simple interest is just this simple little formula. Seriously, memorize this. It'll save you so much time and help you avoid silly calculation mistakes. And speaking of mistakes, watch out for these 3 common traps. Mixing up the formulas, classic mistake. Forgetting that interest can compound more often than once a year is another big one. And, like we just talked about, calculating dividends on the market value instead of the face value. If you can avoid these 3, you'll be in fantastic shape.
So we are going to leave you with one final challenge to chew on. If your money doubles in 5 years with compounding, what was the approximate interest rate? The answer isn't just some number. It's real proof of that incredible, relentless power of compound growth. So take a moment, think it through, and see what you can come up with.